Hello, this is Clint Halstead, and this is an Introduction to Microprocessors Internet-based class. And I'm going to help out on homework 3.1. I'm not going to give the solution to the actual problem, but I'm going to give a problem that's like homework problem number 1. So if you look on the screen here, homework problem number 1 in the textbook called Design Embedded Systems with PIC Microcontrollers, Principles and Applications with Tim Wilmshurst, 2nd edition. The homework problem number 3.1, it says for the following schematic diagram, which is on the screen, complete the timing diagram. I added a little bit of detail here. In the book it just talks about data bus. These are data bus, but I designated them as data bus 1, data bus 0, and then external pin 0, external pin 1. So the data bus 0 is connected to the D input of the D flip-flop, and then the output of that, the Q output, is external pin 0. And then data bus 1 goes to the D input to the Q output of external pin 1. And notice that both the clock inputs to both registers are identical from the standpoint of a logic standpoint. They both have this read-write signal and port select, and then they have the AND gates. So from that standpoint, they're identical. So we're just going to be looking at the bit 0 of the external bit 0. We're not going to look at number 1. But it applies equally well to number 1. But in this case, we're just going to simplify it. Okay, so in the book they have a little bit slightly different timing diagram. This one's a little bit simpler. It's easier to understand. Okay, so the way this circuit works is in order to enhance the understanding of how the circuit works, I added an extra signal called X, which is not in the textbook. Now, I added X here. Now, the reason I added that is because it's going to make it quite a bit easier to analyze what's going on here. So we know that the read-write signal is read is active high, write is active low. So when this read-write signal is high, we know that the microprocessor wants to do a read. When the read-write signal is low, then it wants to do a write. Now in this case, since this is the diagram, figure 3.1 is the diagram of the output stage, the output circuitry inside of the PIC microchip controller. So we know that this circuitry is for an output. So writing is appropriate here, not reading. Okay, so this is a write circuitry. This circuitry is designed for writing, which is the same as saying it's an output circuitry. Okay, so we know that this circuit should output some data when write is low. So one way to think about that is if you have a 0 here at the input of this inverter, you're going to get a 1 at the output of the inverter, and then you're going to have a 1, and then if port select is a 1, then the AND gate, both the inputs will be a 1, which will give a 1 on the output. Now that 1, when it goes from low to high, since this is a rising edge triggered flip-flop, as soon as that edge rises and goes from low to high, then you're going to transfer whatever is on the input at data bus 0 is going to be transferred to the output on external pin 0. So that's the basic function of how it works. To show that a little bit better, well, to show it on the waveform, let's draw it here. What I'm going to do is I'm going to help illustrate this by drawing a horizontal line here. So whenever this read-write line goes low, first we want to model, see what does the X signal look like. Okay, the X signal is just the invert of the read-write. Okay, and don't forget that of course down here that this is actually read-write, so the write is inverted. We want to not forget about that. So since the inverter here is let me fix this signal. Okay, so since read-write is just inverted version of that signal. So X is an inverted version of read-write. So what we're going to do is we're going to draw a waveform of just the inverse of read-write. So let's draw that really quick. Okay, so we go to shapes up here. So an inverter means that, okay, this signal is high, so an inverter is going to give you a low on that. So we're going to have a low all the way up until this point. Now remember that the inverter is going to have a little bit of a delay, so let's add a little bit of the delay. There's going to be a little bit of delay. So when the input of read-write goes low, okay, when it goes from high to low, there's going to be a little bit of a delay, maybe 1 nanosecond or something. Then it's going to go high. So you're going to get the inverse. So let's draw that. Okay. So it's going to go high after a little bit of a delay. Now, what we typically do is we use a dashed line to show what's dependent, what causes, what to occur. So we're going to line that up right there. That's going to indicate that this line is causing this signal to go high. There's going to be a little bit of a delay. Okay. Now the signal is going to be low for quite a while. So let's draw that in here. Okay, we'll draw it. You can see that these signals are exactly inverses of each other, but there's a little bit of a delay. So let's draw that. So after this signal goes high, the X signal is going to go low, but there's going to be a little bit of a delay. So let's draw the delay here. Okay, come in here, and we'll take we'll draw this low. Oops, I got the wrong symbol. I want to get there we go. That's going to go low, and then it's going to stay low. Okay, so now you can see the X is exactly inverted from the read-write signal. Okay, so now except for you got the delay. So now we know that the clock input here, in fact, to make it even easier, we could actually draw that in as well. Just make everything easy. Okay. So let's come over here. Here's the clock input. Let's just call this clock. Okay? And then down here we can call this clock. And we can, okay. Oh, sorry. Okay. So let's call this clock. Just to make it a little bit easier, I like to label everything when I first talk about it. Okay. So we know that clock signal is just an AND gate off of X and port select. So let's look at X. Okay, let's highlight those if we can. I don't know, let's have X and port select. We'll just color those red for right now. So we're going to be looking at X and port select. Now clock is just simply the AND of those two signals. So AND means they both have to be high in order for this clock to be high. So at what point along this, let's copy this signal. Let's take this this little wire here. I'm going to extend it up to these. Let's just take this and move it across here. At what point are X and port select both equal to 1? Well, no, they're both 0. They're both 0. Okay, now we have X is a 1, but we still have port select is a 0. Okay, now we have both of them being a 1. Remember, the AND gate's going to have a little bit of a delay, so let's go ahead and show that. So clock is going to be 0 up until about right here. Okay, that's going to be a little bit of a delay. Now, whenever this one goes high, then we need to make the clock signal go high. Okay, so this is going to go high, starting at that point. Now how long is it going to stay high? So let's look at X and port select. It's going to stay high until here, and then the clock signal is going to go low. But there's going to be a little bit of a delay on that going low. So let's just put it right here. Everything always has, all logic has a little bit of a delay. So you always have to add a little bit of a delay. Okay, so it's going to maybe come to here, have a little bit of a delay. Then it's going to come down. Now let's look at X and port select again. Okay, X is 1, but port select is 0. So that means clock is 0. And then X goes low and port select is 0. So throughout the rest of the signal, clock is going to be low. So let's just draw that in. So the rest of the time, clock is simply going to be low. Okay, so now we can evaluate the D flip-flop. We know exactly what D looks like. D is the same as data bus 0. So if you go over here, the D input to the flip-flop is the same as data bus 0. So over here we can say, actually we can say data bus 0, and we can also call that D. So those two are the same. Okay? Data bus 0 and D are the exact same signal. So the question is, what's going to happen to this flip-flop? Now also notice that external pin 0 is the same as Q. Actually, we should probably designate this D0 and Q0 because we don't want to confuse it with this one. Okay? Oops. Let's see if we can get that on there. So we'll call this maybe D1. We'll call this Q1. Okay? So now that means that this is D1. Oh, I'm sorry, D0. And external pin 0 is the same as Q0. Okay, so those two are the same. They're just being renamed. So if you did a little bit of research into how D flip-flops work, that's not for this course. That's for a digital design course. This course in microprocessors assumes you already know how a D flip-flop works, so you may have to do some research on how a D flip-flop works if you don't understand it. But the way it works is pretty much whenever the clock signal goes high, whenever you have an edge, and so usually the way I show the edge is I want to, oops. Well, we can take this signal actually, and we can format it, and we can put an arrow on it. Let's see. I don't know if it's really beginning or no, it's ending. There we go. Close. You can see here that this edge, and we'll take another one of these lines, copy, paste. We'll line it up with this. This edge is going to cause this flip-flop, this D flip-flop, to do a sample. It's going to cause it to make a decision at that point. This D flip-flop, the Q output doesn't change until this clock edge rises. Whenever it rises, it transfers whatever is on D to Q. That's all that happens. So when the clock edge rises, whatever data is on D gets transferred to Q. So at this point in time, what is on D? Well, what is on D is a 1. So at that point in time, a 1 is going to get transferred into Q. So let's draw that really quick. So that means that at that point in time, now what do you think is going to happen? Well, there's going to be a delay. There's always a delay. This is called a propagation delay. Okay? So after a little bit of time, then this signal is going to go high. Okay? So let's draw this signal going high. And then, since we don't see any more rising edge clocks, rising edges on this clock, that means that once it goes high, it's just going to stay high for the remainder of the time because there's no other clock edges. So that means that the Q is never going to change at all. So this is just going to go high and stay high. So that's pretty much the way it works. Now you can probably have a better chance of doing the homework problem. Now if you had another clock over here, say at this point, that went from low to high, then it would clock in this 0, and so this would change to 0. But in this case, we only have one clock, so that's not going to happen. And again, remember, the clock is made up of X and port select. So you have to make sure that you analyze X and port select in order to get your clock signal. So that's really all there is involved in solving homework problem 3.1. And thank you very much.